is defined by consecutive values having a common difference. All right. Whenever we identify something as having a common difference, we know it's a linear relationship. We could come up with the equation of that linear relationship using the model that we used in the last part of the unit. F of x is equal to a times x minus h plus k. A is your common difference. So once you identify what that common difference is, you already know your A value. All right. And then h and k is just some point on the graph. Now, we plot, if we were to create a graph out of this, we plot the position against the value at that location. But, we don't really have the room for that. So what I'll do is I'll just write the ordered pairs. We would have 1, 1, 2, 4, 3, 7, 4, 10, 5, 13. All right, so these are the specific values that would make up the graph. If I were to plot these, I wouldn't connect them, all right, because there's nothing that exists in between the actual values. So there actually is no meaning to a decimal in terms of the position. If I say something is a position 1.159, it's like, what does that mean? Somewhere in between the first and second position, I suppose, but if our only possibilities in terms of positioning are these discrete values, then it would have to land on a whole number. All right. So what I can do here is I can just choose any one of these points, and that would be my HK. So I'm going to take 3, 7. Doesn't matter which one you take. That goes in for H and K. So f of x is going to be equal to, we have our common difference. I mean, it's pretty easy to see that we're adding 3 every step of the way. Plus 3 to get here, plus 3 to get here, and so on. So my common difference is 3. X minus 3 plus 7. And you can verify this pretty easily. Just take a number and plug it in. So if I want to just verify that the first value is going to be 1, I would replace the x here with a 1 and see what I get. 1 minus 3 is negative 2. 3 times negative 2 is negative 6. Plus 7 is equal to 1. All right, so it checks out. All right. But you wouldn't need to use this model in order to figure out the next term of the sequence. The next term of the sequence is pretty clearly a 16. Because we're adding 3 every step of the way. But if they ask you what's the 97th term of the sequence, you could still do it just by adding 3 over and over and over again, but you'd have to keep track. You got to be careful about that. But you could also just plug in the position for x and go from there. All right. But one thing that we do have to make an adjustment on is, instead of using f of x, the function notation, we're going to use sequence notation. So we're going to write this as a sub n is equal to 3 times n minus 3 plus 7. All right. So that's the quick adjustment from what we've been doing to what we are doing. All right. Because the function notation allows for all the decimal values of x that exist between whole numbers. So you could have irrational numbers, you could have fractions, other kinds of decimals, right? This notation, it's the universal way of saying no, just the discrete values, right? Just the whole number value starting at 1, all right? And so we make a statement of the domain. That's supposed to be a semicolon. It always looks like a J, but n greater than or equal to 1. All right, so this would be the rule for the sequence. So knowing this rule would allow me to get any value for that sequence. All right. So I did something similar here in this table just to kind of really drive the point home, but it's really just kind of rehashing everything I just said. All right, so let's jump down to number 1 at the bottom there. Write and label the first 3 terms of the sequence. They give you the rule here. All right, so I need to come up with the array of values that result from substituting into that rule. So if I look at this as a sub 1 being the first value, a sub 2 being the second value, and a sub 3 being the third value, I could just run a substitution replacing the n in my expression with 1, 2, and 3. All right, one at a time, of course. But so a sub 1, because our function or our relation here is 2n minus 1, so a sub 1 would be equal to 2 times 1 minus 1. All right, 2 times 1 is 2, minus 1 is 1. So a sub 1 is equal to 1. All right. A sub 2 would be 2 times 2 minus 1. 2 times 2 is 4, minus 1 is 3. For simple equations, you probably wouldn't even think to use a calculator, but you start getting some funky decimals involved in terms of your relationship, then the calculator becomes handy. And I'll show you that in a little bit. A sub 3 would be 2 times 3 minus 1, so a sub 3 is equal to 5. These are the first 3 terms of the sequence, 1, 3, and 5. So from this, I could actually use the trend that I see to come up with any value after that. They didn't ask for it, but if I needed to come up with the 10th value, I'd say, all right, I got 1, 3, 5 seems like odd numbers, so 7, 9, 11, 13, 15, 17, 19. 19 would be the 10th value in the sequence. All right, but noticing the trend allows us to do that. You need at least 3 computations in order to get that trend, because you have, you could say that this is a plus 2 going from this value to this value, but if it doesn't hold for the next term in the sequence, it may not be arithmetic. This could be what's called geometric, so that ties together with exponential functions, where instead of adding 2 to get from 1 to 3, you could be multiplying by 3. So if the next value, the third value in the sequence, instead of being a 5, if that were a 9, then I would know that I'm looking at a common ratio rather than a common difference. All right, but in terms of actually crunching the numbers, it's really not that bad. All right. So in the next one, it's just saying find the third term, so that's a sub 3. So replace the n with a 3. So negative 9 plus 5 is negative 4. Third term of the sequence is negative 4. All right. Now, if you haven't picked up on it, when you're given an arithmetic sequence, the slope, I mentioned this before with the other notation, but in this notation, it's also the same idea. That slope is your common ratio. All right. So in order to find multiple terms in a sequence, if you know the slope and you know the first term, you can figure out everything else. All right. So in number 3, they're saying write and label the first 3 terms of the sequence. So a sub 1 would be equal to 5 times 1 plus 1. So a sub 1 is equal to 6. But then I look at this and I say, okay, well, I have a common difference of 5, which means that all I need to do to find the second term in the sequence is add 5. So a sub 2 is going to be 11, because all I did was I added 5. A sub 3 would have to be 16 by the same reasoning. Right? But we tend to want to do the straight computation if we get too far down the line in the sequence. Right? And if we're only asked for a single term, it's really not that bad to just do it by hand. All right, so the 12th term in the sequence, a sub 12, negative 12 plus 6, result negative 6. 8th term in the sequence, a sub 8, 1/2 times 8 minus 3. So 4 minus 3 is going to give me a 1. All right. But like I said, you could do it in a calculator. Like, for example, that last one, I'll just do it fairly quickly. So you go into y equals, you type in your relation, but you type it in as a function. So you just got to know to ignore any of the decimal x values. But they don't show up in the table anyway. So a sub n is equal to 1/2 n minus 3. So I'm going to type in 1/2 x minus 3. So I'll put it in as 0.5. 0.5x minus 3. All right, so same expression, just using an x. Then go into the table and just look for the 8th value. All right, so it's set up as whole numbers, so we're good to go. The 8th value is the number 1. You have the whole sequence here. If you needed that too, you could just jot all those values down. All right, but the 8th value is 1, and so you'd have it right away. So for a multiple choice question, it's not a terrible idea to do something like this. All right. So on the next page, we get into formal definitions. Yeah. So a sub 1 represents the first value of the sequence. The d value is the common difference. Between consecutive terms. And the n value, really, I mean, it's talking about the location within the sequence. So you could say position within the sequence or location within the sequence. All right, so location of any value in the sequence. If you find these 3 ingredients, then you'll have your explicit formula for a sequence, specifically an arithmetic sequence. Little typo for somebody else. This should have a semicolon followed by n greater than or equal to 1. All right. That part of it, the statement of the domain always has to be there. If it's not, then it's not 100% correct. All right. So I need to identify the a sub 1. A sub 1 is the first value in the sequence. Usually pretty easy to identify, but sometimes they'll give you part of a sequence, just not at the beginning. They'll say that the first value in the sequence is 13. Oh, I'm sorry, I meant to say the 11th value in the sequence is 13. The 12th value is 15. What is the rule for this sequence? All right, they won't tell you what the first value is. You'll have to kind of work backwards to get there. But in this case, it's not bad. The first value is clearly a 5. Then I'm looking for the common difference to get from one term to the next. Looks like I'm adding 4. Then I just ask myself, is that happening consistently? Across the board, every time I take a step from one term to the next, I'm adding 4. So I have my common difference of 4. That's the common part of common difference. So 4, and so we could just write our rule. So a sub n is going to be equal to a sub 1, 5, plus 4 times n minus 1. N is the location of any value in the sequence. We want to leave that variable. We want to have the option to find any value that we want, as long as, semicolon, n is greater than or equal to 1. All right, so if you find the first value and the common difference, everything else is going to remain the same. So in the next one, the first value is negative 7. the common difference, looks like we're adding 3 every step of the way. So common difference would be 3. It's really the same thing. The structure is always going to be such that you're going to have a need to find whatever the a sub 1 value is. Then you're going to find whatever the d value is, but everything else is going to stay put. I mean, it's just basically fill in these boxes, and you'll have your explicit form. Let's put that there for the next one. So the a sub 1 was -7. The d value is 3, and that's it. All right. The reason why we have a 1 in here is because this version of the formula, we used the linear equation formula on the previous page. This variation of it assumes that you're only using the first value in the equation. All right. So it kind of makes the one that we had on the previous page a little bit better, but this is what they want for the region, so here we are. All right. For number 8, a sub 1 is equal to 1/2. D, again, just thinking about how we get from one term to the next, it looks like every step of the way here we're adding 1/2. And if you're unsure what the value is that you're adding, just subtract 2 values in the set. All right, second value minus first value, for example, and that'll give you the common difference. All right. So in this case, we have the initial value of 1/2 and the common difference also of 1/2. So this would be my explicit model. All right. You got a blurb about something called recursion. Recursion is the process of choosing a starting term and repeatedly applying the same process to each term to arrive at the following term. Recursion requires that you know the value of the term immediately before the term that you're trying to find. It's kind of a wordy explanation, but it honestly, I don't know that it tells us much in terms of process. It tells us a little bit more in terms of theory. The 3 parts of a recursive formula are, well, you can see it in the example here. The initial value, so the first term of the sequence, all right, then a sub n, which represents the rule for the sequence, that's the rule that'll give you any term of the sequence depending on what n is, all right? And then the last thing would be the domain. And that domain applies to the n value. So when we're trying to come up with a recursive formula, these are the 3 ingredients that we would need to find. So if we could find them, then the battle is won, because there isn't really much more than that. All right. Now, listing out the terms of the sequence, the notation is kind of funky, but it is very manageable. So they're telling us that the first term here is a sub 1 -4. Now, they also give us a rule. That rule says a sub n is equal to a sub n minus 1 plus 5. All right. Now, in terms of like everyday speak, what that's telling us is that the previous value, that's what this represents, plus 5 will give you the next term of the sequence. So I'll just say the next value. And even that's a little kind of worded weirdly. But if you're talking about a single value in a set or in a sequence, there must be a value that came before it. All right? Or at least theoretically. It may not actually be in the sequence, but there is a value that, if you follow the rule, must exist. What we're looking for is the relationship between those 2 values. What this is saying is, if I take the value that comes before me in the number line and add 5 to it, then you'll get my value. All right? So if I'm saying, like you got 10 people standing in a room and each person has an age that differs by 5 years, right? And I tell you that my age is 45, then the person standing to my right would have to be 50. The person standing to my left would have to be 40. All right? So you could, just by knowing that difference or the relationship from term to term, you can easily come up with the values. Or you could do it computationally. So a sub 2 would be a sub 2 minus 1 plus 5. All right, just following the formula. If I want to find the second term of the sequence, a sub 2, 2 going in for n, would be equal to a sub 2 minus 1 plus 5. Now, a sub 2 minus 1 is the same as saying a sub 1. So this is calling on a previous bit of information. All right, because a sub 2 minus 1 is equal to a sub 1, and we know a sub 1 is equal to negative 4. Therefore, negative 4 plus 5 will give us the value of a sub 2. All right, which is 1. So I now know that a sub 2 is equal to 1. All right. Now, if you look at the difference between what we had before and what we have now, negative 4 became a 1. It became a 1 because we added 5 to the negative 4. So if I want the next term of the sequence, if I'm doing it by hand, I would type or type in a sub 3 is equal to a sub 3 minus 1 plus 5. A sub 3 minus 1 is the same as a sub 2. A sub 2 is equal to 1, and 1 plus 5 is equal to 6. So therefore, a sub 3 would be equal to 6. You could show the work, and sometimes you have to, depending on the way a question's phrased. Yeah, using a recursive model, find the first 4 terms in the sequence, show all work. Regents question. As opposed to, what are the first 4 terms in the sequence? And it's just like an everyday question. All right. So the last one, they want the first 4 terms. So the last one would be a sub 4 is equal to a sub 4 minus 1 plus 5. A sub 4 minus 1 is a sub 3. We now know that a sub 3 is equal to 6. So we're looking at 6 plus 5, which is 11. So therefore, 3 dots in the form of a triangle means therefore a sub 4 is equal to 11. So I have the 4 terms of the sequence. Negative 4, 1, 6, and 11. But, again, depending on how the question's phrased, if you know the first term and you know the relationship between terms, so a sub 1 is equal to 6, I need a sub 2, 3, and 4. And this is telling me that if I want the next term of the sequence, all I'd have to do is take the previous one and subtract from it 8. Then I have everything I need, because I'd say, okay, well, I want a sub 2, so I'll take the number that came before it, 6, and subtract from it 8, I'll get a negative 2. If I want a sub 3, I'll take the number that came before it, subtract 8, and I'll get a sub 3, which is negative 10. If I want a sub 4, I take the number that came before it, which is a sub 3, which is equal to negative 10, subtract 8 from that, and I'll get negative 18. All right. So, like, it's the definition of, like, we can do this the easy way or we could do it the hard way. Like number 9, showing all the work, a free response question on the Regents exam, like, you might have to write all that stuff. But if it's just show the first 4 terms of the sequence, it's really not that bad. And you can verify that this is correct by taking the 6 and adding to it a negative 8, doing it again. So in my home screen, 6 minus 8, negative 2, do it again, negative 10, do it again, negative 18. All right. The thing about this topic that makes it so weird is that you already know this stuff. It's just you know it by a different language. All right, this sequence notation is really the only thing that makes it challenging. All right, because all we're doing here is working with linear equations, writing the equation of a line over and over again. All right. Writing a recursive model from an array of data is actually even easier, because all you would need to do is identify the initial value and the common difference. All right. So the initial value is 5. The common difference is 4. So plus 4. So if I take the previous value and add to it 4, I'll get the next value in the sequence. But I also have to make a statement of the domain. So n greater than or equal to 2. So each one of these problems is going to have the same structure, in the sense that I need to identify the first term and then the common difference. Right? So I'm starting off with a -7. Then to get from a -7 to a -4, I have to add 3. If you know it's arithmetic and there is a common difference, then you're good. You'd only have to do it for the first one. But I recommend verifying that it works every step of the way. All right. Sometimes it's obvious, sometimes it's not. All right, but we're just taking a sub n minus 1 and adding 3 to it to get our next value in the sequence. All right, so for 13, again, the first value, 1/2, we say, how do we get from the first term to the second term, from the second to the third, third to the fourth, and fourth to the fifth? It looks like we're adding 1/2 every step of the way. All right. So previous value plus 1/2 gives the next value. So if you interpret the rule correctly, then something like number 14 is very easy. An arithmetic sequence is given using the recursive definition. They use D's instead of A's. It's really not a big deal. It's got the same structure. They're telling us that the first value is -4. So this is the first value. And this here is the common difference. Common difference for short. It's really common difference between consecutive terms in a sequence. That's kind of a mouthful. So if I'm looking for D sub 4, well, I have D sub 1. I want to go 3 more steps out into the sequence. So my first term is -4. I want to then add 3 to that. That'll give me a -1. Add 3 again. That'll get me to a 2. Add 3 again. That's going to get me to a 5. So D sub 4 is equal to 5. All right, so just adding 3 repeatedly. Then the last one, given a sequence defined by the explicit formula, write out the first 3 terms and then create a recursive definition for the sequence. All right, so they wrote it in function notation. That's perfectly fine. It really means the same thing. So f of n is equal to -2n plus 8 is the same as a sub n is equal to -2n plus 8. All right, so it's the same a different notation to represent the same thing. So if I want to list out the first 3 terms for this one, all I'm doing is plugging in a 1, 2, and 3 to this function. All right. So if I plug in a 1, and you can do it in a calculator if you want, but if I plug in a 1, I'm going to get a 6. If I plug in a 2, I'm going to get a 4. And if I plug in a 3, I'm going to get a 2. And you see we have a common difference of -2. All right, but I need my 3 ingredients for the recursive model. The first value in the sequence, the rule for the sequence, and then the domain. First value here is 6. The rule for the sequence is take the previous value and subtract 2 from it every step of the way, and you'll get the next term of the sequence. And the last thing is we make the statement of n greater than or equal to. That's for all cases, right? Unless it's like a trick question. But really, what that's just telling us is that this rule only applies to n values that are 2 or more, because we already have a sub 1. We don't need a rule for that. We know that value. We need a rule that'll give us a sub 2, 3, 4, 5, and 6. So it's only for the values of n that are greater than or equal to 2. All right. I wanted to take a second and show you how you could come up with the linear equation on your graphing calculator. All right. So I'm going to create an example 16. All right. Try to just bang it out real quick. But let's say we have terms of a sequence 1, 4, 7, 10. And we want to come up with an explicit model. All right. Basically, all it is writing the equation of a line. So this would be my first term of the sequence, my second, third, and fourth. By the way, typo. Anytime I add a new example, that's a typo. So L1 and L2 is where you'd store this data. So we're going to approach this the way we would for an exponential regression, except we're not going to use an exponential regression. All right. So stat edit to type in your data, your L1 values, 1, 2, 3, 4. Your L2 values 1, 4, 7, 10. All right. So you do all this by stat edit. Type in the data. Then you go to stat calc 8. Stat over to calc, right arrow to calc, and you'll see option 8 if you scroll down. It says linreg a plus bx. That's the most consistent formula in the calculator that's related to what we're doing in class. So as long as it says L1, L2 here, you can go right to calculate. The R squared just tells you the strength of the fit. If it's 1, it means it's a perfect fit. But what this is telling me is y is equal to a plus bx. But in this case, y is equal to -2 plus 3x. So my rule, my explicit rule, is a sub n is equal to -2 plus 3n, where n is greater than or equal to 1. All right, so I'm able to get all that from the calculator without doing any computation. Doesn't seem like a big deal, and in fact for linear cases and arithmetic sequences it's really not, but when it comes to more advanced stuff, using regressions is going to be very helpful. All right.